Hello everyone, it's Amir Hossein Khajapur, and our paper's name was Exploring Website Fingerprinting Attacks on Tor Traffic in Realistic Settings, which we briefly call Deep Inside Tor. So we are a couple of students from Sheffield University of Technology and in the INL laboratory. Here is the outline of this presentation. Firstly, I'm going to briefly talk about contributions, and then some previous works. And also afterward, we will talk about some background over the Tor non-entity network. I mentioned our methodology that was used, and the datasets, experimental results, and finally the conclusion. So in terms of contributions, we changed the Tor client and OpenSSL library to achieve the most accurate labeling process that's been proposed so far. And as a result, an extensive dataset consisting of Tor-generated network traffic resulting from a crawling of 100 domains was achieved, which was mainly for multiple scenarios. For example, in one scenario, just one website at a time was crawled. On the other one, multiple crawls was simultaneously working. Or even we also have datasets that's just dedicated to the web pages of the domain, or we have also some datasets that's being crawled for inner pages of the same domain and not only the web page, which we call website fingerprinting attack compared to web page fingerprinting attacks. Also, we have datasets just for applications data. We automated all 10 applications, 10 desk applications, and recorded the labeled traffic, which was tunneled through the Tor source and Tor network. And additionally, we also introduced another type of fingerprinting attack, which is called cell fingerprinting. And cell is a unit of transmission in Tor network. And in this new attack, we didn't use the packet, we just used the cell. And finally, to verify the safety of the Tor security and encryption, we employed the convolutional deep neural network and random forest and showed that the tests hardly exceed those of random classifier. And this kind of indicates that the Tor encryption is indeed safe against this state-of-the-art deep learning attacks. So just to mention some previous works, back in 2011 was almost the very first work that tries to do website fingerprinting attack in onion routing. And they were mostly using the classical machine learning like SVM. And so they could find accuracy up to 55% and compared to the 3% which was done in earlier works. But the point is that all of them were using just the scenario in which the victim only opens one single page or uses one application. And in this new one, which was for 2018, they kind of tried to pivot to the settings in which the victim is actually running different tabs in browser or different applications at the same time. But the point is that they mostly will rely on finding the endpoint in which adversary opens the second tab and discarding all the intertwined traffic. And so again, they were classifying the traffic which belongs to the single web page, and they could achieve almost 65% true positive rate. And again, like in different area, Jaffer et al. In 2022, which is recently proposed, they were kind of trying to let people know that the encryption itself might not be always safe, even if it is being used for over 2 decades. So they just crawled 100 websites and they could gain accuracy of over 15% for just the encrypted payload of the network and without using any metadata. So it is just the encryption itself and nothing else. So they kind of could contradict the common belief that the encryption itself is not secure sometimes. So it is one of the initiatives for this work, and we wanted to verify that this sort of attacks are not applicable in the Tor encryption. Okay, so in terms of background on Tor anonymity network, here is a very high-level overview. Tor is a SOX proxy with super low latency from the end user perspective. Users send traffic through the heavily encrypted path called secrets in Tor network. And as already it's been mentioned, the units of transmission in Tor network are cells. We have different types of cells: relay, create, and extends are some of them. And the cells that's being targeted for labeling are the relay cells. So path or circuits in Tor network usually consist of 3 nodes. And the reason is that by increasing number of nodes, we gain no more security or privacy. And so 3 nodes is just more than enough now. Here is the picture of encryption of a single cell as it goes on in the path. So the procedure is the exit node opens a TCP connection with the target server in the internet. And in forward direction, each cell is encrypted 3 times at the beginning corresponding to each node. And on the backward direction, each node adds a new onion skin on the cell and moves it through the circuit back to the client. In this work, we only focus on the backward direction. And so in this case, finally, the exit node on the forward direction, the exit node should give the application data to the target server. And on the backward, the entry node gives the cell with multiple layers to the client. So as is already clear from the picture, in the state number 4, the raw data is being encapsulated within 5 different encryption layers. One is the very inner layer, which is colored by the red. It is a TCP connection between client and server. There are 3 more encryption layers, which are onion skins. Any of them is for any of these nodes. And there is another red circle on the very outer layer, which is the TLS connection between client and node, or a node with another node. So we have 5 different encryptions, even for a single cell. And the onion skins worth to mention that they are all AES with CTR mode and with 128 bit. So it is data structures that's being used in the Tor client to store all the data from network. So the TLS decrypted data for each connection is stored in an instance of a buffer structure called buff_3, buffer_t. And then each buffer is also a queue of chunk_t instances that are filled with the data and the data is added to the queue. So when sufficient data has been accumulated in the buffer, an instance of cell will be created from the head of the queue, and its onion skins will be decrypted one by one after filling the cell. And finally, the relay cell's content will hand over to the user application. For our different attacks, we employ 2 different adversaries. One of them is the local eavesdropper, who can observe the network packets between the user and the first relay node, which is the entry node. So here we shows the location that the adversary is eavesdropping by the red arrow. And we call this attack as a web fingerprinting, but we proposed a new type of fingerprinting attack, which is self-fingerprinting. And in this new scenario, the attacker could be any of the nodes inside the circuit, not a local eavesdropper. And so as a result, you can see that this entry and middle node are exposed to less encryption layer in this attack. For getting data set, we have different labeling challenges. And the main challenge is because the processes are, when they're working together, the traffic is mixed, And so the TLS packet label is not clear also unless it's revealed by the client because we are capturing the backward direction. So because of that, instead of labeling the packet, we should label the cells beforehand and then label each packet with its corresponding cells. And therefore, we record two pieces of information for each relay cell, the website and application name, and the encrypted network traffic corresponding to each cell. So in order to do that, we modify the OpenSSL library so that it returns the raw TLS records that it reads in addition to the decryption, in addition to the decrypted data. And finally, when we have all these two information for any of the cells, we search through the packets for the encrypted payload and the PCAPs. And upon finding any exact sequence bytes for cells encrypted data in the network packet, we label the packet with the same label as its corresponding cell. So, but in this case, there could be multiple situations that makes it a little bit more complicated. For example, as already clear in the picture, each packet may contain multiple cells, so it should receive multiple labels. And at the same time, each cell can be broken into two packets, as it might start in one packet and end at the other one. So the result is that you should label both packets with the same label of the cell. It's also worth mentioning that since the ordering of the cells and the corresponding packets are almost the same, so the searching process is not that much computationally heavy. And as already mentioned, in the self-fingerprinting scenario, the entry node is exposed to just 2 layers of encryption and the middle node just 1 layer of encryption. And also for the exit node, there is no point to doing the fingerprinting attack because he or she already knows what's the target server address. And also in this self-fingerprinting attack, there is no need to deploy any node because we can have all these necessary data inside the client itself. And so we can gather the data set by just having captured the data between the client and the entry node. And also there is no need to change the OpenSSL library, obviously. So to generate our dataset, we use two Ubuntu systems running at the same time. And one important point is that to have the most accurate labeling process, we only took 23 consecutive packets as a batch. And we found out that it is large enough to encompass as many packets as possible and also at the same time small enough to not to contain too many packets from different sources. And also we only label each batch only if there is one label inside the batch whose proportion is higher than a certain threshold. We took two different dimensions while gathering the dataset. One of them was the degree of parallelization, and the other one is whether the victim is only surfing a single web page or just an entire website. And so according to these two dimensions, we could gather 7 different datasets, which almost all of them has 1.5 million packets per batches for websites and applications. Afterwards, we ran some experiments over our dataset, and as you can see, the accuracies were just mostly for verification of the dataset, but at the same time, we found out that LSTM combined with CNN could achieve almost 3.23%, which is quite significant, knowing the fact that these data are just random data, randomly distributed, and they should be encrypted. So I would say that there is space for future works to investigate what's happening actually. Probably there is some lack of there's some information leaking in some parts. So here is a conclusion of our work. We have explored the idea of fingerprinting Tor network using the encrypted payload of the network packets. We captured multiple extensive datasets, used various methods to conduct the attack, and our results at the end of the day shows that Tor's encryption system is kind of immune to such attacks. And so the dataset is also publicly accessible, and specifically compared to the other available datasets, ours benefits from two main advantages. Firstly, if we use a very novel technique that's for labeling packets are much more accurate, and we could capture the setting that in which the adversary is running multiple, or you can just have arbitrary number of applications running at the same time. And also our dataset contains the actual network packets and their encrypted payloads, which is usually summarized or removed in the other work. So that's all. Thank you for watching this presentation.